lecture title.
So in this last lecture, I want to discuss single boundary wormholes. Yesterday we talked about multi-boundary things that you get by looking at products of observables in two copies of a theory. And today I'm going to start by talking about single boundary wormholes. And depending on how fast this goes, I think we'll have plenty of time to sort of wrap up and discuss some of the open problems and questions that I think are raised by a lot of this averaging from the point of view of the Bootstrap. So by a single boundary wormhole, I mean higher topology configurations with ordinary ADS boundary conditions. So these are geometries that you might call handles. In 2 dimensions, they're easy to draw. This is an example of a single boundary wormhole in 2 dimensions, just a handle. It's a higher topology contribution, in this case to the thermal partition function of the 0 + 1 dimensional boundary theory. In higher dimensions, they're harder to draw, but for example, in 3D, we could take ADS3. So this is H3 drawn as a ball, and carve out two smaller regions inside that H3, and then glue them together. So this is like this is a 3-dimensional version of this. So those are the kinds of geometries that I'm talking about. But before we get to that, I want to go back historically to work of Sidney Coleman in '88. So Coleman argued that if you include wormholes, and these are the kinds of wormholes that they have in mind, wormholes with ordinary single copy boundary conditions, that if you include wormholes in quantum gravity, then you get some exotic effect to refer to as alpha parameters and the universes. So an alpha parameter means a random coupling constant. Now this is not a random coupling constant in the sense that we've been discussing so far. What we've been discussing so far is a random coupling constant in the boundary CFT. And what Coleman was talking about was a random coupling constant in the theory of gravity, like in the bulk Lagrangian. So the basic argument there is that if you have a gravitational theory, call that Z bulk, and you include some wormholes in the path integral, then you expect to get something like this. You have the ordinary bulk, phi is the bulk fields, including gravity. Then you have the ordinary bulk Lagrangian. But suppose you have some microscopic Planck-sized wormhole that connects distant regions. And furthermore, suppose that the endpoints of that wormhole can be anywhere. So that these two wormholes, they can end anywhere. This is not an on-shell calculation, this is an off-shell calculation. So Coleman imagines integrating out the wormholes. And since these endpoints can be anywhere, the effect they'll have, the result in the effective theory after integrating them out, is that you'll get a bilocal interaction, integral dx dy, of some operators that join the ends of the wormholes. So call that sum over I, OI of x, OI of y. So the idea is that this is what you get by integrating out these Planck-sized wormholes. And now you can integrate in a random coupling constant. So we're just going to take this bilocal interaction and reinterpret it by integrating in an alpha parameter. So now we have an integral over alpha, e to the minus sum over I alpha I squared.
Sorry, so there is no kernel into this?
There's no, sorry?
No kernel?
No, the idea was that, and this was a guess, an ansatz, was that these could end anywhere, and since the bridge that joins them doesn't really care where the endpoints are, that it wouldn't depend on the separation. Okay, so I'm just going to rewrite this as integral dx L minus alpha I OI of x. Okay, and you can easily check that integrating out the alpha parameter gives you back the bilocal interaction. The interpretation here is that alpha is a bulk coupling constant. Well, I'm calling it bulk. Of course, he wasn't talking about ADS CFT, just some theory of gravity. So this is a coupling constant in your theory of gravity. And then we're integrating over, we're averaging over that coupling constant. So there's a classical probability distribution for the value of that coupling constant that we're integrating over. Now, when you have a classical probability distribution like this, you have two choices. You can think about it as an ensemble of quantum mechanical theories with a classical probability, or you can think of it as one big quantum mechanical theory that includes all of these possible values of alpha, and think of alpha as labeling a superselection sector in that one big quantum theory that includes all of them. Okay, so this is the rough idea. Now this argument is off shell, so it's UV sensitive. You know, it assumes that there's some physics at the Planck scale that we don't understand that stabilizes this and gives this particular contribution to the path angle. Now this idea was, well, back in the 80s, this was mostly abandoned. It was sort of uncontrolled. It wasn't clear what it was leading to. It was mostly abandoned, but it's been revived recently in the context of the JT gravity. And what we're going to see is that there's a similar effect in 3D gravity that can be interpreted in the Bootstrap language that we've been discussing. Yes?
Sorry, is O a field in terms of phi, or is O?
Yes. Yes. Yeah. It's a bulk operator.
So we
Yeah.
understand the components work in a following sense that if we start with this path integral description with alphas, that should be interpreted as wormholes. But if you have wormholes, then you do not necessarily have Gaussian measure of alpha, and it should be more complicated measure.
Well, he claimed there was a, he claimed, do you mean you want to put a kernel here? Or,
Well,
I mean, if this is the kernel, then it's Gaussian.
right, well, I mean, I do not, yes, I wanted to know if wormholes only correspond to this kernel, or there could be possibility of kernels. And he only gave us one example, the simplest one.
Yeah, if you imagine that there's some interaction between the two mouths of the wormholes, then you get some kernel and something more complicated will happen. But if you have a kernel here, I'm not sure you can interpret it in terms of alpha parameters though, right? Any probability distribution that I put here, I think is going to lead to something without a kernel. Okay.
Anatomy is referring to maybe a three-mouth wormhole.
Yeah, if you have, yeah, that's right. That's right. And there's a paper by Banks back from then where he talked about these multi-wormholes where you do get non-Gaussian terms in the probability. So, I want to start by revisiting a calculation that we discussed before. which is the 4-point function O2 or O1, O2, O2, O1. And we're going to be doing this calculation for defect operators, which, remember, just doesn't mean it's not a special kind of operator. It just means that they're not black holes, they're below the black hole threshold. These subthreshold operators in the large C ensemble. And when we talked about it so far, we said, well, in a holographic theory, this is approximated by the identity block. 1, 1 goes to identity, goes to 2, 2, mod squared. Approximately. And we said, well, this is nice because this matches what you expect. This is nice for two reasons. First of all, it matches what you expect from the bulk, which is a picture with two conical defects, one for operator 1, and the other one for operator 2. Okay, so the action of this gravitational solution matches this identity block. And furthermore, we were happy because it matches the Gaussian average in the dual channel. That is, this is equal to the sum over heavy states with H greater than Hi greater than C over 24 of the dual exchange times that OP coefficient 1, 2i squared and this holds after averaging. Okay, so that's what we discussed before, and that sounds nice, but we've neglected a term, and that's the term I want to talk about now. So the term that we neglected is the contribution of light states on the right-hand side. We're considering a theory that has some collection of subthreshold operators. For concreteness, let's say there are just 3 of them. Let's say there are defect species 1, 2, and 3. We could add more, won't affect anything. Then what we've dropped here, contributions from those light operators on the right-hand side. So those need to be included. We're missing contributions like 1, 2 goes to 3, goes to 1, 2, mod squared, C1, 2, 3 squared, average. And it can't just be that it can't just be that the OP coefficients are 0. We know that these OP coefficients are not 0 because yesterday we calculated them by a wormhole. We calculated C1, 2, 3 mod squared average.
Just a terminology issue. So the defect operators were operators with H less than C over 24, but over C.
Correct.
Light operators, I thought, were H over the 1.
Sorry, I think I might have been using the language wrong. By light, I just mean subthreshold.
So even over the 1.
No, I'm only talking here about operators of order C. Everything is order C, but light, I meant to say
Below the black
subthreshold. Yeah, thank you. Okay, so it can't just be 0 because we calculated it yesterday. This average was given by the 3-point wormhole, and that we calculated as action, and it was this universal function C0 squared. Okay, so for this whole story to hang together, we need to find a new bulk contribution that accounts for this exchange of the subthreshold operators. That'll be the handle. So if we go back to the bulk, let me write this again, O1, O2, O2, O1, as calculated in the bulk by the gravitational path integral. The first term is this one. I'm going to change the pictures, I'm going to change the way I do the pictures a little bit because it gets very confusing to draw these wormholes in 3 dimensions. This is a 3-dimensional picture. These get hard to draw. I'm going to draw them as 2-dimensional pictures instead, like Witten diagrams. Okay, so this first one is the identity block. So that's just a redrawing of this 3-dimensional picture here. So I'm now drawing as a Witten diagram. Well, it's a Witten diagram, but with back reaction, because these operators are order C. And we need to find another term. Okay, so the other term should have the same boundary conditions. So we should have the operators 1, 1, 2, 2 inserted, and there should be a single ADS boundary. And we can draw such a contribution like this. Okay, so it's the same boundary conditions. You insert operator 1, 1, 2, 2, but now we send them through the wormhole. And we need a third operator. So the third operator goes here, looping through the handle and never touches the boundary. So first of all, this is a solution of 3D gravity. I think I'm not going to get into detail about that, but I'll just tell you briefly how that salad point is constructed. Well, there's a hint for how you should construct it. The reason that we needed this diagram here is because the wormhole exists, right? That's what we said a minute ago. That wormhole tells us this contribution must be there, and you can kind of see the wormhole here. The wormhole has been glued into this diagram, so you can kind of see it playing a role there. But the fact that this is a saddle means that we should find a saddle that looks like that. And in fact, you can get from here to there by taking a quotient of this geometry that sort of starts with the wormhole and then glues together two surfaces that look like this. And if you think through it, you'll convince yourself that when you glue this diagram like that, you get that diagram over there.
Tom, can I ask a question?
Yeah.
How do you know that the second picture gives the leading contribution to the function?
Well, now we're going to calculate its action. And the action of this diagram, e to the minus s grav, this is now a gravity calculation. So the gravity calculation gives the following: C0 of h1, h2, h3 mod squared times the Virasoro block 1, 2, 3, 1, 2 mod squared. Well, this is a classical calculation, so it really only gives the exponential part, the semi-classical Virasoro block. So I'm not going to do that gravity calculation here, but this is what we get. And that agrees exactly with the term that we said we were missing in the CFT side.
So
looks like a very tough computation. Can you demystify a bit how we would do it?
You mean how the
geometry with a wormhole? You need to compute the action. It looks.
How to calculate the gravitational action?
Yeah.
Yeah, there's a trick. So this is done in 2 steps. Let me see. Yeah, it's actually not that bad. The first observation is that if you cut this diagram here, then the thing running in the middle is operator 3. And if you calculate the stress tensor, so you do this by a semi-classical word identity. You calculate the stress tensor at the boundary here, using that diagram. And then you show that that stress tensor has the correct monogamy, that the stress tensor corresponds to the correct monogamy problem for the semi-classical block. And the way of doing that is just by looking what's running in this cut. And what that tells you, that calculation, just looking at this monogamy problem, gives you this part of the action. It doesn't fix the constant for you. So now you have the block up to a prefactor. And then you can take a limit where these things become very far apart in order to fix the prefactor. And when you take these very far apart, it just gives back this diagram. So then you can borrow the result of the wormhole to get C0 squared.
Can you say a few more words about this stress tensor business? So this is about computing the expectation value of the stress tensor on this geometry.
Yeah.
And it captures the exponential. I would imagine that it should capture that result divided by the expectation without stress tensor, and the exponential would drop. Is this naive? I mean, in other words, an expectation of a stress tensor is not an exponential quantity, right?
No, what you're really doing is there's this auxiliary problem that you can, the monogamy, so the monogamy of the solutions of these equations is used to calculate the semi-classical block. There's some auxiliary problem. This is Zamolodchikov's procedure to calculate large C conformal blocks, is that you can get it by studying the monogamy of this differential equation. And so what you need to do is check that the monogamy properties of this differential equation have the right, basically that the solutions of this equation have the correct monogamy to correspond to this block.
And this equation comes from Einstein gravity.
Well, it comes from Zamolodchikov, but you rederive it from Einstein gravity in this picture.
How?
And match it.
Can you just say, what's the basic idea of deriving this equation from Einstein?
Yeah, so let's look at this picture instead, because this is the same diagram. What you need to do in this picture is the Brown-York stress tensor at the boundary here needs to be integrated around this operator, needs to be calculated in a loop around this operator. And the fact that you start without the quotient, and then the monogamy corresponding to go around this loop has to be the monogamy of the operator that's enclosed. So that's gonna tell you that this equation has the monogamy corresponding to the operator that's enclosed. Now when you take the quotient, you don't change the geometry. So after taking the quotient, it's still true that the monogamy problem around this loop corresponds to the dimension of that internal operator. So that's it, you're done. And now you know that your stress tensor corresponds to the correct monogamy problem. And that gives you a derivative of the on-shell Einstein action. Now you integrate that equation to learn that the answer is this up to a constant, and then you just have to fix the integration constant.
Maybe you explained yesterday, so please tell me. But what is the physics? What is this monolith? You're talking about some monolith?
No, I didn't explain that.
Is it a big detour? If so,
It's a big detour.
Okay.
Yeah, maybe let's talk about after. Yeah.
I have a question.
Yeah.
If I took operators 1 and 2 to be the same, would I also have contribution where there are only 2 operators that go through the handle, rather than with the third one, when this geometry is ever present?
Let's see. Sorry, what do you want to do? You want to take?
Like without a green line. What happens if I
No, that's not a solution. See, the reason this is a solution is because if I chop it here, then well, if I just look at the handle part and I chop it down the middle, that's a hyperbolic 2-manifold because it's a 3-punctured sphere. If I only had 2 defects running through, I wouldn't be able to find a solution.
Okay, so is this related to, I mean, one could ask, how do I average over a scaling dimension, for instance? Does this have any, because, I mean, I would like to average over 2-point function square, but the 3-point function square is that possible?
Yeah, I'm coming to that. Well, no, sorry, for the 2-point function of local operators, we don't know any way of doing that with wormholes. But I'm coming to a similar question in a minute.
So what's a metric of this wormhole?
Of this wormhole?
Yeah.
So the metric, the way to get the metric is to start with this metric, which I wrote down yesterday, and then take this quotient. Now that's not quite the metric you want because the boundary metric will not be flat. You get a single boundary but with a crazy metric on it, and then you have to do a control mapping to make it the flat metric.
You have to do some surgery for the wormhole metric.
Yes, although when you once you set up the problem, you don't actually have to you don't have to find the control mapping explicitly. It's enough that it exists.
So you add this C123 in the D channel, which correspond to something in the F channel?
Yeah, I wasn't going to talk about the dual channel, but that's right. So we said the identity block in the I've gotten S and T confused. The identity block in one channel was the Gaussian average in the other.
Yeah.
And indeed, once you include these other operators in that first channel, you need non-Gaussian, that corresponds to some non-Gaussian corrections to the averaging in the dual channel. So this is one example of where, as you iterate this, so you start with the Gaussian ensemble, but as you iterate this and solve more crossing equations, you need to start including non-Gaussian corrections. This is an example of that. So let's compare this to Coleman. First of all, there are some differences. Coleman was off shell and had this very simple bilocal ansatz for the effect of the wormhole. Here we're on shell. So that's an advantage in that we can completely control this calculation. It makes the final answer a little bit more complicated. So this wormhole, the endpoints of this wormhole are not free to move around. This is one particular saddle point. This is frozen somewhere by solving the equations in motion. But we can ask what this tells us about the bulk theory. So it's easy to see that this is equivalent to adding a bulk coupling lambda 1, 2, 3 for the massive particles. So if you recall yesterday, we just had the Einstein action plus the world line action of the particles. There was nothing there that allowed the particles to interact with each other. But what this wormhole does is it effectively allows the particle, it gives an effective interaction between the particles. So we could add a bulk coupling lambda 1, 2, 3 for the massive particles and average it. The way I like to think about this is to stare at this wormhole and imagine that you pinch the handle. Okay, so if you stare at this wormhole and imagine making the handle skinnier and skinnier until it basically pinches away, then this diagram looks like it just looks like a Witten diagram for the exchange of that particle, and then there's a handle that joins the vertices of the Witten diagram. So as far as the representations that are running in the intermediate channel and the kind of interaction that's being induced, it's just like the Witten diagram for the exchange of particle 3. The reason you need to average over, so you add this coupling, the reason you need to average over it is because the 3-point function itself should just be 0. So this is lambda 1, 2, 3 average just gives 0, whereas the Witten diagram for 1, 2 goes to 3 goes to 1, 2 should give lambda 1, 2, 3 squared average, and for that we don't want to get 0, we want to get that wormhole. So this average, this variance should be chosen to be the same variance that we had in the dual CFT in order to get the right answer for that wormhole. In other words, we can either include the wormhole in the bulk, or we can include this random bulk coupling, which is the kind of picture that Coleman had in mind. You have an effective theory description where you include random couplings in the bulk.
Sorry, Tom. This picture here, pinching the wormhole, I guess is probably also what would effectively happen if you separate the points a lot, right? If you bring
Yeah, that's right. Yeah.
and then your argument is how you would fix the normalization then and the gravity computation. By this argument that you just said, right? Because you want C0 square, then you would put the C0 square on the...
Well, it's a bit better than that. So this diagram, if you allow it to back react, is the conformal block. Like forget the handle. If you just have a network of conical defects like this and you allow it to back react, you get exactly the Virasoro conformal block. Yes, we can fix the constant by taking them very far apart, but we get the answer for any values of the cross ratio.
Sorry, is that because the external dimension is heavy, so you get conformal block instead of the written diagram? Because a written diagram is not a conformal block, it's a...
No, that's right. It's because the particles are heavy.
Yeah.
It's a bit like the GD's equivalent diagram story.
Yeah.
So what's the reference for this geometry for the back reaction, for this network back react?
I don't remember the reference for that, but it's cited in our paper from March.
Okay.
Okay. Now there's another consequence of these type of wormholes that I want to discuss. So suppose you have an operator V, which is not a local operator. It's some big operator formed by inserting a bunch of local operators. Now, if V creates a black hole, then there's a rough expectation that operators like V, or correlation functions like V prime, where this is two different such operators, should be e to the minus s suppressed. This is like an exclusive amplitude for a process that involves black hole production in some intermediate channel. I want to partially confirm this through these single boundary wormholes. I'm going to start not with two different operators, V dagger and V, not with two different operators, V and V prime, but with an operator and its conjugate, V dagger V. Okay, so when we calculate V dagger V, there's a contribution, say it's that 4-point function, there's a contribution that's one of these handle wormholes. Let's see if I can draw it. Okay, so now we want to have, I want all 4 of them to run through the wormhole. 1, 2, 3. Okay, this is also an on-shell solution of 3D gravity, and it's similar to the one we were discussing before. The difference, however, is that the intermediate channel here is not some other light operator, but the identity operator. Let's take these operators to be separated by a distance d. Now the funny thing about this diagram is that as d goes to infinity, this does not factorize. Into V dagger V, because there's a sorry, I think I'm saying that wrong. I'm getting confused. 1 sec. Okay, so what I want to think about in particular is the case where V is charged. If V is a charged operator, then let's say you have operators O1, O2, O3, O4, and on the other side you have O1, dagger, O2 dagger, O3 dagger, O4 dagger. Then with a wormhole like this, you can calculate this contribution. And what I want to suggest is that the interpretation of wormholes like this is that they tell you about these exclusive amplitudes, and that in particular they tell you about how global symmetries have to be violated in quantum gravity. because we can take these operators to be charged so that they have zero overlap with the vacuum, but we can still get contributions like this and use them to calculate the magnitude of these exclusive amplitudes. Now, a funny thing about this is that if I take the operators to be different, so if I say I did 01, 02, 03, 04 over here, and on the other side we just had 4 different operators, 5, 6, 7, and 8. In that case, you still expect some contribution to the exclusive amplitude. You still expect it to be e to the minus s. You expect to be able to make a black hole and spit out 4 different particles. But you don't get a wormhole like this. The wormhole really requires V and V dagger in order to join the lines. And I think the interpretation of that is that the exclusive amplitudes, if these are 2 different sets of operators, then those exclusive amplitudes come with unknown phases. They come with some unknown sign or phase. And so when you take an average, they drop out. And that's why the low energy effective theory doesn't seem to know about those. It doesn't seem to know about the wildly oscillating exclusive amplitudes. You calculate, it seems to know about the average. So when you calculate it, you get 0. Whereas something like this, where you have something that's positive, something that's reflection positive, then it has to come with a plus, and so the average is something non-zero, and then the low energy effective theory seems to know how to calculate it. So this argument used the bulk. I'm drawing these bulk diagrams. So it doesn't explain from a CFT point of view why you can't have global symmetries in quantum gravity. I'm not trying to say that. I'm just saying that this appears to be a way to take statements about, statements like that from gravity and translate them into CFT language. So this is the kind of effect that we should think about if we want to imagine how to bootstrap the no global symmetries argument from the boundary point of view.
So, before we raise this quick question, so yeah, a lot of the previous pictures could be understood from covariant tail in some channel gives you something in other channel. This does not.
Yeah, I don't know of any way to interpret this one that way.
Okay, so it's really novel thing about this picture.
Well, sorry, even for the 2-boundary wormhole, I don't think there was a Tauberian interpretation of the 2-boundary wormhole either. There was a Tauberian interpretation for stuff of of just spherical topology.
Yeah.
So the trivial topology, all that stuff was just Tauberian rewritten.
Okay, great. That's the picture. Okay.
Yeah.
My other question is about this exponential.
This one?
Yeah.
Yeah.
So normally, okay, that suggests that these effects are suppressed by M Planck or something related to the dimension of the external guy.
Yeah.
But could there be any situation where the classical action is 0, so that we get power suppression instead of exponential? Is it conceivable?
I think it's conceivable, but it won't be a saddle. I mean, right?
Yeah.
I think in that case it's hard to know whether it's UV sensitive. That's what happens in the spectral form factor, that it's almost a saddle, but the action is 0. But in cases like...
I mean, the saddle means that the dirts around the action
Yeah.
large. Doesn't mean that's not a statement of the value of the action.
Right, but do we trust the contribution of a can we use the saddle point method to calculate the path integral if the action is 0?
If the curvature around it is steep, yeah, it doesn't matter what the value of the action is. About the dirts around second
That would be nice, but I don't know.
Yeah,
I don't
there's no
know.
example.
I don't know an example. No. So, yeah, I I guess one point I wanted to make here was that I think that although I'm drawing these pictures in 3D gravity, and I've taken some sort of exotic example model here where we have these heavy defect operators and everything, but I think what I'm saying here is probably totally generic and doesn't really require this particular model. We're talking about averaging. I think anytime you have an operator that can create a black hole in any number of dimensions, you can probably find wormhole solutions like this, solutions of the Einstein equations that give you contributions to the exclusive amplitude. So we could, like in the case of 3D gravity, I was taking these operators to be relatively heavy so that they would back react, and you only need 4 of them to make a black hole. But another thing we could do is we could take order C of them, and we could take them to be truly light operators with dimension of order 1, but insert a large number of them that's order C, and again that operator will be big enough to create a black hole, and I think you'll be able to get contributions from the gravity side that look similar.
Sorry, why do you need 4? You need 4 because they are subthreshold.
3 would have been enough. I just did 4 because I felt like it.
How about lack of errors, but with some wave packets that give them a big energy in the bar?
Well, there's no. Yeah, there's 2 kinds of black holes that we're talking about here. There's operators that are already black holes in Euclidean that make a black hole at time 0. These operators are of that type. Now, another thing you can do, like you say, is insert a wave packet, and those things will collide and make a black hole in Lorentzian. I don't know how to find saddles like this for that type of black hole, but I suspect that there might be some kind of complexified saddle where you go on a Schwinger-Keldysh contour into Lorentzian where there's a black hole, make the wormhole, and then come back. But
it's about technically harder, but in principle it should also exist with the 4 lifetimes.
With high momentum, that would be my guess, but nobody knows how to make those wormholes. And I'm not certain that they should be on-shell solutions like this one. It could be that might require doing something a little bit more elaborate or doing the path integral or something.
Is it strange that 2 operators are not enough?
Well, I think that's a related question, that 2 operators probably are enough if you give them some momentum so they can collide. The reason they're not enough in 3D gravity is just because you can't make this hyperbolic manifold. So I think it's sort of the same question. You have to understand how to deal with the collision in the Lorentzian signature, and then maybe you could get it to work for 2.
Sorry, Tom. So you're talking about these being charged. Are you talking about global symmetries of the CFT or global symmetries in the bulk?
I was talking about global symmetries in the bulk. See, if we gauge the symmetry in the bulk, then this handle will get canceled by summing over fluxes, and there will be no contribution like this if we gauge the symmetry in the bulk.
From the point of view of the CFT data, what you see here is that there is some, I mean, if I were to take this 8-point function and decompose, I would see that there is no identity at, up to exponentially small correction in C, so there's e to the minus C in front of the identity block. Is this how the global symmetries are violated?
Yes.
So then, so if I take only 2 operators, and 2 on one side and 2 on the other side, and I would like to exchange the identity, that would want to be proportional to the 2-point function. So how do I make that into the minus C subpress with just a normalization?
Well, for a 2-point function, you can't draw this picture for a 2-point function.
Yeah,
so
I know.
It doesn't work.
Yeah.
I mean, I don't know how to. You can't. The problem is you can't make a black hole in Euclidean with 2 operators. So.
Right, but this seems to be related to the picture. I was trying to understand if there is an argument from CFT why this should be.
Oh, from CFT?
Here, like the identity being exchanged is proportional to a 4-point function, which could just be small. and it's normalization independent. But the 2-point function being small, that's not the sensible thing to ask.
I see. Yeah, I don't know the answer to that. Okay, what I want to do now is just sort of wrap up the whole series with some outlook and discussion.
Sorry, I'm a bit confused about this picture.
Yeah.
So these operators O's are charged, right? You said.
Yeah.
So then the expectation value of just V is 0, right? So they are charged. If I take just O1, O2, O3, O4, it's 0. Is it true? Or?
Yes. Yes.
Yes. Okay. So then we have something that's 0, and now you construct an average, and you say the average is naively not 0, but so what was the puzzle about this no global symmetries? We wanted it to factorize, but because they have charge and charge flows from one side to the other, the result is not 0, and that's the puzzle?
Yes. Yes. Okay. I want to mention a few sort of general points about the whole story. And maybe I can also solicit some questions from the audience about kind of what the open questions and ideas of things to look at now are. So first of all, why averaging? You know, why is it that we've ended up discussing averages? Are we required to talk about averages, or is this just something that we're doing because it's convenient, or what exactly is going on here? And there are different points of view about this. The one that I've mostly emphasized is that this average occurs because of a low energy, well, one way of thinking about it is that this averaging is some kind of effective description. That Einstein gravity is the low energy theory, it doesn't know everything about the UV, so we do some averaging and then we get the low energy description. So there's been some aspects of the UV that have been forgotten or coarse grained over somehow. Exactly what that coarse graining is, I think we don't fully understand yet. But in that point of view, which well, in that point of view, I think that the point of averaging, the purpose of averaging is to remove some sensitivity to the UV. So there are some observables that are UV sensitive, but when you average them, they become universal. This is something that's very familiar, say, from StatMech or hydrodynamics. And we're trying to do the same thing for gravity. But what we don't know, and I think an important open question to think about, is what exactly the question is, well, okay, there's certain universal things we seem to be able to extract either from gravity or from averaging, but what is the universal stuff? What is the universal information in conformal field theory that holds on average? You can ask that question either about non-holographic CFTs or you can ask it about holographic CFTs. A good guide in this is looking for physics that's determined by black holes and Einstein gravity. So those are the universal sector that we can find in holographic theories. And anything we find in Einstein gravity ought to have some kind of universal description in CFT. There's another point of view on why averaging, which has been emphasized by Schlenker and Witten, which is that averaging is a necessary feature of taking large N limits. This one I haven't really talked about, but I just wanted to mention. So when you take the large N limit of gauge theory, there are, if you think about low energy states, then it makes sense to choose a particular light state, and as you take the large N limit, that state sort of retains its label. So you can take a particular state and take the large N limit and track that particular state as N goes from 1,000,000 to 1,000,001 to 1,000,002, etc. But the same is not really true of black hole states, black hole microstates, in a regime where the theory, where the spectrum is chaotic. If you're talking about black hole microstates, nothing's protected, so it's they're separated by e to the minus s. As you go from n equals 1,000,000 to n equals 1,000,001, they jump around in some crazy way. And it doesn't even really make sense to say, well, I was looking at that state and taking the large N limit of that particular state. It doesn't even really make sense. So the proposal is that it's that large N jitter that's responsible for averaging. And if that's the right way to think about it, then anytime you have an effective theory of the large N limit, that effective theory is very natural for it to have some averaging going on. How else could it describe, if gravity can talk about those microstates at all, it must only be able to talk about them in some averaged way, because you can't identify them in the large N limit.
So, could you please clarify this point? Any finite but large N doesn't require averaging, but infinite N is sort of is good average theory.
Yes. Sorry, what was the question?
If I have large but finite N,
Uh-huh.
I can avoid having averaging, right?
Yeah, you just have some list of numbers, and that's your list of numbers, and in principle you can avoid averaging.
And on the gravity side, I will not have wormholes then?
Well, I think the right way to think about the gravity side, and this is a bit vague, but I think the right way to think about the gravity side is that you should either include the wormholes or the microphysics. Not both. That the wormholes are summarizing some contributions from the string microstates, and depending on what, you can use either picture. You can either include the wormholes or include the microstates.
So that's what I try to understand. Normally, if I want to have finite but large N, it means I need to include 1 over n squared corrections, and perhaps infinite number of them. So that means that on the gravity side, I need to calculate loops, and once I calculated loops of gravity, I don't have to worry about wormholes.
Well, no, I think once you start doing a 1 over n squared expansion, you're expanding around n equals, doing some expansion around n equals infinity. I think if you do it that way, then you probably need to include wormholes. But say you could do the exact string theory at finite n, then I don't think you're supposed to include wormholes. You just do string theory, and there's quantum states, and you include them, and in principle, you shouldn't have to also include wormholes separately.
But I wanted to approach finite but large N by calculating all terms in the 1 over n squared series. That should be possible, right?
Should it? Is that a convergent expansion? I don't think that. Maybe you can get arbitrarily accurate that way, and I think there's probably sort of two different ways of doing it. There's sort of a bottom-up way where you start at infinite n, and you start including corrections, and as you include more and more corrections, you get a more and more accurate answer for the microstates. But then there's another picture where there's some fixed set of states, and you don't do any averaging or include any wormholes.
Yeah. I'd like to make a comment about, there's one situation where I think we may actually know how to do this split between very UV stuff and light stuff. It's a VV version, it's not as complicated as this, because it's a correlation function of 4-point parameters, where, for example, for three-dimensional model, there's this nice formula that you can approximate the correlator very well as a sum of 3 Witten diagrams. That's been studied. And, you just include the Witten diagram using 3 channels for the light stuff. That gives you a good approximation. But it's not exact. And if you try to sum over autooperators in this representation, you overcount it. Right? It's like something that would be null 3 channel, it's just wrong. We know, however, that there's an exact representation where you sum over particle Frege blocks in just 2 channels, and then somehow the UV tail of that sum reproduce the light stuff in the 3rd channel.
Yeah.
But there's an alternative, which may or may not be an adequate solution to what we're looking for, which is this crossing symmetric dispersion relation that I can do. I believe the starting point is this sum over 3 within diagrams, but somehow managed to give you an exact representation. It starts with what you want, but is exact. Which sounds a bit surprising from this perspective. Because here, right, the splitting is not, it's still an open question, like how you, in the gravity setup, how you avoid overcounting.
Yeah, that's right. Yeah. Yeah, I don't know. Thanks. Yeah.
But yeah, this crossing symmetric dispersion relation may somehow achieve this, or maybe I'm missing something about it.
Maybe. I mean, it needs to be all. It all needs. Yeah, I guess that's an exact formula. Right.
Yeah, it's an exact formula.
Yeah. Yeah.
Let me briefly mention higher dimensions.
So there's no story of there's no story like this so far for higher dimensions in terms of averaging OP coefficients and getting bulk wormholes out of it. In principle, and the reason for that is that it was important that we had Virasoro. Okay, so what Virasoro allowed us to do was it allowed us to solve all the light sector. So there's some effective theory in the bulk which is not chaotic. We're working an approximation where that's just gravitons, and in the boundary that's just Virasoro. So by using Virasoro blocks, we were able to sort of factor out the non-chaotic sector, and then just average over the UV stuff that's left over. So if you were to try to do this in higher dimensions, then I think what you would need to do in principle, this sounds very hard, is first solve you need to factor out the non-chaotic part. So you sort of need to first solve this problem of getting the low energy effective theory perturbatively in the bulk. All the stress tensors and the multi-stress tensors, and extract that out, and then average over the UV microscopic part that's left over. I don't think there's really a hope for doing that in complete generality. We're not going to be able to solve that in closed form. But what we can do is look for simplifications and situations where that can be done in various limits. For example, a lot of the techniques that you have in two-dimensional CFT apply also in higher dimensions in the light cone limit. Things like the Tauberian theorems you can apply in the light cone limit. Things like this universality of getting gravity from CFT apply in the light cone limit. So that's a place to look. That's maybe a place to look for some overlap between these ideas and gravity in higher dimensions. There are wormholes in higher dimensions, which are sort of similar to the ones that I've been describing, but they're not created by local operator insertions, at least not the ones that we know how to write down. The wormholes like this that we know how to write down in higher dimensions are spherically symmetric. That's just a matter of being able to solve the Einstein equations in more than 3 dimensions. If there is one lesson of all this from the Bootstrap that I want to close with, it's that we should think about applying the Bootstrap to multi-CFT observables. Now, the observables in multiple copies of a CFT obviously don't contain any more information than the observables in a single copy of the CFT. But as far as the analytic techniques go, it reorganizes that information, as we often see in the Bootstrap. It reorganizes that information and might make it more accessible to us humans. And there are many precedents for this in math, going way back to the work of Hardy and Ramanujan and others, where they were interested in modular objects, and often the way to learn about these modular objects is to study multiple copies of them. And the kind of analytic techniques they use in math to study modular forms rely on some very similar tricks to the ones that I've been using here, where you take multiple copies and look at averages, etc. So I hope that we can bring that into the Bootstrap. All right, let me stop here. Thanks.
General question. So you showed us nicely that if we take an average of CFTs, specifically high energy, the high dimensional operators, we get a sort of low energy triviality. Now, on the other hand, and also there are some, in order to get contribution from some other operators, such as this tree defect operator 3, you need also to include some Hartman solutions, which apparently lead to they lead to global violation to the global symmetries in the back. Now, let's take another logic. So we know that using just gravity, Einstein gravity, there are good arguments, black hole remnants, many others, which point with gravity, you don't need to invoke string theory to do that. That tells you that the global symmetry should not be, they should be all broken in a quantum in a gravitational field. So if I take that logic, then this effect should not be there. Because, as you said, I can't have any global symmetry in the bulk, everything should be gauged, and if I gauge, your wormhole won't be there. So on the other hand, from the safety point of view, you do have that contribution. So if I take this other point of view, how should I look? Should I say that I shouldn't really average, or this seems to be some sort of a puzzle, or something else will cancel this contribution? Yeah. What is the...
No, it's a great question. I don't really know the answer. I think what these pictures suggest is that there's some tension between having global symmetries in the bulk and the kinds of things we expect from chaos and ETH in the boundary CFT. And perhaps that can be turned into an argument that chaotic CFTs can't have bulk global symmetries. But that's just a hope. We don't know how to run that argument.
Question? I'm actually confused. Do you think that the wormhole is sort of a UV stuff, or it's IR?
I think it's both. I think a wormhole. Let me start with an easier question. Is a Euclidean black hole a UV thing or an IR thing? Okay, so we can use the action of a Euclidean black hole to calculate the entropy, which is UV counting, but it's clearly an IR thing. And I think wormholes are similar. I think wormholes are a low energy summary of some microscopic UV information, and some effective description of that UV information. Now, I think an important question is exactly how much does the low energy theory know about the UV completion, and that's well, we have to understand how to include all these wormholes, which ones are reliable, and what we can extract. Yeah.
Did I understand you correctly that actually in 3 dimensions you can put a numerical bound on an effective operator that violates any global symmetry? So that's not what you can calculate.
Well, this is a bulk calculation.
Yeah,
I think
but
there's-
say what if in 3D would we know, what is the lifetime of proton? What is the upper bound on the lifetime of proton?
Yeah, I think we could calculate that using this wormhole.
Like you didn't try, like what is enough? Because people sometimes argue, okay, what is it? Exponentially suppressed, but what is the number in the
What is-
exponent?
No, we didn't try the proton. We've calculated some of these diagrams, so I guess we've done some analog of that for three heavy defect operators in ADS3 or in CFT2.
What's the scale in exponential? I mean, it's going to be x of minus n times square, but divided by.
Yeah,
Is it scale, or is it something that you got scale, or what is the scale? It is in the action that you have. What's the scale?
Well, what sets a scale is the entropy of the. There's some intermediate black holes in this 4-point function. Or sorry, if you make a black hole by inserting these 4 operators, then there's an entropy of that black hole, and that's what sets the exponential. It's not literally e to the minus s because these are heavy operators, and that's an estimate for random states. But it's something e to the minus number times s.
But the proton is light, so I guess it's a different calculation.
Well, for the proton, what you would need to do is to you need to insert enough operators to make a black hole. So you would have to look at like the million-point function of the proton in order to make a black hole, and it would be the entropy of that black hole showing up there. You wouldn't see it if you looked at the 4-point. If you look at the 6-point function of the proton, you're not going to see this. But I think you might see it if you look at the million-point function.
It gives them enough energy.
Well, if you give them enough energy, that feels like it should work, but I don't know how to do then we get back to this problem of constructing Lorentzian wormholes, and I don't actually know how to do it.
Yeah, the scaling with the mass of the proton is different from what you described, is distinct from the usual EFT picture, where you write some, I forgot what's the mass dimension of the proton decayver, dimension 8 or whatever, and then the dependence on mass of proton is set by the mass dimension of that thing. But to suggest that you describe here, the number of proton you need to make a black hole depends strongly on the mass of the proton. It's not the same scaling at all. Maybe a different calculation. But yeah, the calculation you did were like for every stuff.
Yeah, that's right. Yeah, let's see. I don't know how that would scale. Once you did that, you'd have to look at a very high point function and then rewrite it into the effective theory.
Are there more questions? No? Let's thank Tom again.